And now it's time for Ag Geek Speak with
GK Technologies,
Sarah and Jody.
In the fields again, I just can't wait to get in the fields again. The life I love is spreading potash for my friends, and I can't wait to get in the fields again. No, I can't wait to get in the fields again.
Welcome back to Ag Geek Speak. Last week, we had John Breker on with us from AGVISE Laboratories. We were having such a great conversation about different soil testing methodologies. I think we ended our conversation talking about acid soils. We're very excited to have John back with us today, and we're going to keep talking about, well, we're just going to keep geeking out about soils because it's a lot of fun. And so here we go. So John, thank you. Welcome back.
It's good to be back.
With that, I'd like to just ask, okay, so we finished up last week talking about, the very last conversation we had was about soil acidity, liming. The conversation that we had before that was calcium carbonate equivalencies. And I think that starts to bring in a really good place for us to talk about variable rate and the idea of maybe even zone and grid sampling and where we might be able to find some of those soil pH differences in a given field. So I'm just going to kind of lob that back up again. That's kind of getting to be my favorite word there, lob that back up, and let's have a conversation about zone and precision agriculture soil sampling. John, what have you seen from just the trends of precision soil sampling over the years?
Well, in my short career, it has continually gone up. And when you start looking back when precision ag as a real concept started in like the late 80s and early 90s, it has only gone up from there. And I don't think that should surprise us. For any of us who work in the precision realm, we see field variability all the time. And we know that the good Lord didn't lay out soil types in squares every quarter either. So as we see these landscape variations, whether they be eroded hills or ridges, low areas, depressions, this is real variability on the landscape, and we farm that variability. So as people have been able to take advantage of that, precision soil sampling, whether it be grid or zone sampling, has only gained in popularity.
When we were talking last week, we had talked about, when we're dealing with acid soils, and I'll ask you too, like, what are some ways that we can look for that, or what are some general trends or areas where we might find that? But how do we actually go about managing that too? And where does that precision soil sampling come into play to do a better job or just help us manage these acid soil areas?
I think, well, we should look kind of historically. 10, 15 years ago, I don't think we were talking about acid soils in North Dakota very much at all. Really kind of when I started was about some of the first times that we were starting to see some questions about this coming from areas in Southwest North Dakota, North Central Montana, North Central South Dakota as well, and some of these long-term no-till areas. And people were just noticing weird things in fields, and they were troubleshooting these by taking good soil and plant samples and then finding a nearby bad area, taking soil and plant samples from them. And then they were noticing, holy cats, we got pHs that are at 4.8 here in North Dakota. We never talked about acidic soils like that before. So over the past, decade, people have become more and more aware of this issue whenever they run into these low productivity areas. Maybe before they just brush it off as maybe a saline soil or something like that. Well, now they're finally figuring out that they have some acid soils. And even when you look at whole field composite soil test data, there are those that are below 6 all throughout the Northern Great Plains. Not, I would say it wasn't super common, but when you start drilling into some of these certain geographies, they're a lot more common than a person would think. So first step, I think, is get into some zone sampling to actually tease out where you can find some of these areas on the landscape. And when you get to pHs that are, less than 5.5, certainly closer to 5 or 5.2, that's where aluminum toxicity starts to come into play, and that will take plant biomass basically down to nothing. And so you will notice these areas of reduced plant growth It also affects herbicide activity. So you might run into areas that have worse weed issues because those herbicides are unable to work properly. Plus, you have reduced regular plant growth, so you don't have the competition. So some of those are easy little red flags in your field to say, hey, I should maybe start looking at these acid pH issues. So you can either work with some more dialed in zone maps, because some of these areas are still very big, but they're often a little bit more patchy than typical soil nutrient relationships on the landscape. So actually these acid soils are a really good argument for grid sampling, and I would say as small as 1 acre grids. Now, I'm not saying we're going to do 1 acre grids across the whole landscape or even across every field, but you can, with zone sampling, actually pinpoint some more acidic zones and then grid sample within them, so you can use a bit of a hybrid grid and zone concept. So that way you can come up with a more fine-tuned lime map, which last time we were talking about pH and buffer pH. That pH regular test will tell you if you need to apply lime. It's that buffer pH test will tell you how much lime to apply. And that's going to vary across that whole field, just like any variable soil parameter. So with those tools, that's kind of my short answer to a very complex question.
So I just want to bring up one of the really interesting things that you just said about the idea of grid sampling within a zone to try to identify where soil pH issues might be occurring. It's a very interesting concept, and yet I am aware of agronomists who are doing that very thing. They've got areas in the field that they've pinpointed on their zones as being lower productivity, and because of that, they felt that with the soil pH numbers they were getting back, there could be some areas of definite soil pH issues in that red zone. And so they went ahead and they made grids and they grid sampled just that red zone. And they were really able to find some interesting data. So it's very interesting that we're kind of having sort of a theoretical conversation with John here today. And yet in real life, these things are coming to fruition. And it is very exciting to see. So if you've ever had the argument about grids versus zones and which one is better for soil sampling, there you go. Now we can have the conversation about gridding a zone where that's appropriate.
Well, I think we have a really practical example of this too on Jody's own farm, because I know she's played around with this quite a lot.
And I think what's interesting, so like the one field that I have that is, oh my God, it's a funny little mess. That's what it is. But it's a 28 acre field, and historically we'd had really bad issues with yellow foxtail. And the reason I bring that up is because, like John mentioned, there can be indicators that there's something else going on here. And, when I went to college, I'm like, oh yeah, this field's an issue because it's a certain soil type. We probably have acidicity issues. That's what's going on. Until I actually went and split the field into 2 composite samples and found that one came back at like 6.5 and the other came back at 5. That's a little bit low. And typically when we're thinking about acidicity issues, we're looking at pHs above 8.2. So a different problem than what I had in mind originally. But what we had done, in addition to doing a long-term lime trial there and looking at, how long does it take for pH to increase in the top 0 to 3 inches with just surface applying lime in a no-till situation without incorporation, what I did is I worked with Kelly to make a zone map for this field, go ahead and zone map this and collect the pH, like determine what the pH was for each zone. And then also go back and take a Wintex to do 0 to 6 inch samples and on a 1 acre grid to figure out where exactly I needed to apply lime and how that differed with the zone map that I came up with for pH. And what was really interesting is that the grid map came back showing me that I needed a lot more lime than what I was shown in the zone map. And the big reason behind that is when I did do those 1 acre grids, I did have some spots in the field that were pH. Basically what happened is there were 2 spots that were sodic. So they had percent sodiums that were over 5%. But the rest of the field was not sodic, and they had pHs that were much less than that. And so when I was collecting those zone samples, I was likely getting into areas that had a higher pH and we're masking those areas of really low pH. So again, this is a really small example, only on 28 acres, but it's a really good example to show that, when we're trying to put together a quote unquote average soil sample for a large area, we can easily mask the issues that are going on. And it probably won't show us the true extent of how acidic an area is in a field.
So out of curiosity, when you're getting either a composite soil sample or a sample or a soil pH result for a particular zone, what is kind of your trigger pH that you see in there where you think, oh man, we should probably start gridding this out? Because when you get an average rate back, you're going to find it's an average, right? So there's spots that are lower and there's spots that are higher. So what is that average number for a composite soil sample and or a zone where we should start doing a grid sample in there? And is it different between a zone and a composite?
Yeah, I mean, that question is really driven by how variable that field is. I did do a little bit of tinkering with our soil test database to kind of, that might help answer this question. And I looked at a pile of precision sampled fields that we had gotten in both grids and zones, and calculated like what the field average pH would be. So basically that composite pH versus what would be the range of zones or grids within that field that would be below that average value. So one of the values that concerns me, particularly for like aluminum toxicity or for some of our other more sensitive crops like manganese toxicity that can start showing up in canola, I would like to at least manage it above a pH of 5.5, because that's kind of a red flag value for me. So looking at the average composite pHs versus what percent of those zones or grids were below 5.5, if you had a field composite pH at 6, that would translate to anywhere from 0 to 20% of those zones or grids would be below 5.5. If you were at a pH of 5.5, then it's like 50% to up to like 80% of that field is below 5.5. So 6 is the point where you better be starting to get concerned, because that there are areas of that field that are less than 6. But if you are at 5.5, that's kind of a big concerning area where I think you need to definitely look at precision soil sampling and managing those pHs for the sake of pH and acid management in a serious fashion.
I think it's really important to point out too that when we talk about moving from like a pH of 6 to a pH of 5, that's a 10 times increase in acidity. So it might sound like that's a small change, but that's a really big change. So keep that in mind when you're thinking about pH. Even though it's a small increment of an integer, that's a big difference.
Yeah, it's a log scale. Yeah, we don't think in log scales too often as humans, but pH is probably the single most common log scale that we use.
And remember, pH is the power of hydrogen.
So, and one thing too, I want to bring up, because that was something that Franzen we had a conversation with Dr. Franzen a while back, and a couple of things that he brought up were really fun, thinking about grid and precision soil sampling and the history of that, and then also pH. And so power of hydrogen was mentioned, but also like one thing we haven't talked about is the fact that there really aren't any lime sources for us here to easily use in the Northern Great Plains. And that's not only in North Dakota, that's also South Dakota, Manitoba, and the Canadian prairies. And so we do start to talk about implementing these grid and more precise ways of soil sampling, because this is a very finite resource that we're trying to put onto our fields. And I want to bring back a story that Franzen mentioned in the context of like the history of precision soil sampling. So like the I-states, the Corn Belt, they have been dealing with this issue for the past 100 years. And they've known for 100 years now that applying lime does increase soil pH and brings back productivity. And they were first motivated to start breaking their fields down into smaller pieces because they found that when they were going to the train to take back a ton of lime on their horse-driven carriage, that it was very difficult to bring back that much lime and spread that across the whole field. And so that motivated them to break their fields into smaller pieces to make that lime application more manageable. And so that's really what motivated the beginning of precision soil sampling and management. And we are now doing that same thing here in North Dakota because we face the same challenge of trying to get that much lime, apply it, and then also not have to do it over the whole field.
And isn't it interesting that we have issues with low soil pH, and yet we have issues with high soil pH in the same state and in the same area? I mean, it blows my mind how in North Dakota and northern Minnesota specifically, we can be talking about how we should be thinking about managing these low soil pHs in areas. And yet at the same time, we're trying to manage iron chlorosis in our soybeans with these calcium carbonate equivalencies, lime equivalencies, quite frankly, that are high and inhibiting the plant's ability to take up iron.
I'm so glad you brought that up because that's where I was thinking too, is like we can't talk about managing low pH without mentioning the other elephant in the North Dakota room or the Northern Great Plains room, managing high pH. I know that was a common question when I worked at AGVISE. Are there ways that we can manage and reduce high pHs, and what are the things we should consider if we're doing that?
Well, the first question is if you should do it. I know
Amen.
I mean, when you first cover like just soil pH, you got the acidic side on one end, you got the highly calcareous or alkaline side on the other, and somewhere around the middle is where most plants want to be. 6 pHs, 6.5 to 7. It's a nice neutral range. It has the optimal nutrient availability for most nutrients, crops. But we are also dealt with the hand that Mother Nature has given us, and however geology has played out in your local area. So if I had my druthers, would I rather be on a low pH side or a high pH side? I would rather be at a high pH side if I was forced with those two options, because the relative complications are not nearly as bad. Why we are thinking about, wanting to reduce pH on those soils is because we know phosphorus availability is less at high pHs. Zinc availability is going to be less. And if we are growing soybeans, iron deficiency chlorosis can be a real killer. But other than those three options, it's not all that bad compared to being on the low pH side. If you have aluminum toxicity and have to haul in lime, that can be a very serious problem. So anyway, those questions of whether or not we can get away with managing high pHs, I think we can, especially for banding phosphorus, or if we're growing corn, need to put on zinc, we can put a seed placed chelated zinc starter at planting. We have other ways of getting around it. But let's get back to the real question of how can you actually reduce soil pH? And the most common material that is used is elemental sulfur, and that oxidizes to sulfuric acid. I mean, you can use elemental sulfur as a sulfur fertilizer source, but here we're going to be talking about rates that are much, much higher than using it as a fertilizer source. And the actual math behind how much elemental sulfur you need to apply to reduce pH is actually quite simple. And it comes back to our old friend calcium carbonate. Remember, we were talking about that in the previous episode about its role in buffering high pH. Well, for each 1% calcium carbonate equivalent in soil, it takes 6,400 pounds of elemental sulfur just to neutralize that carbonate first. Now, I did not stutter there. I mean, it takes 6,400 pounds or 3.2 tons of elemental sulfur for each 1% calcium carbonate. We're just talking about the upper 6 inches. We're not talking about the carbonate below that. So if you have a soil with 5% carbonate, that is equivalent to 16 tons of elemental sulfur. So just when you run the economics on it, it doesn't get you very far. You can buy land cheaper than that if you really wanted to change soil pH. But again, we have more practical ways to handle these problems with banding phosphorus to increase phosphorus use efficiency, applying zinc where we need it, or if we're growing soybeans on IDC prone soils, to choose tolerant varieties and use a chelated iron starter at planting. So anyway.
Can I ask a question about that 6,400 pounds of elemental sulfur per 1% CCE, calcium carbonate equivalency? Is that this is a theoretical question, but is that regardless of the soil texture that you're in? Does the soil texture make a difference on that?
Soil texture, it doesn't matter because that calcium carbonate equivalent value is reported on a soil weight basis.
Oh.
So you are physically trying to neutralize, 1% calcium carbonate is equivalent to 20,000 pounds of naturally occurring carbonate. So that is what you're trying to neutralize, is 20,000 pounds of calcium carbonate or free lime.
It's
free.
Free lime.
So, we've actually done projects here at AGVISE with applying elemental sulfur to try to change soil pH and manage this carbonate issue. There was a project that got put in 2005, I believe, or a colleague, John Lee, he had put on 10,000 pounds of elemental sulfur. It dropped it down from a pH of 8 to 7.8. So, really did it. So we actually installed another project, that was about 4 years ago now, I think. And there we went up to rates of 40,000 pounds of elemental sulfur. So 20 tons of elemental sulfur, which, if I did my math correctly, should be able to neutralize all that carbonate and then some. So we're still watching it. So far, the carbonate is burning up. So, it just shows elemental sulfur can do it, but it's a very expensive practice and not practical at all.
I think what I'm hearing is that I'm not going to acidify a part of my farm east of Northwood to grow blueberries. I'm just going to wait for AGVISE's 40,000 pound plot to get down to a pH of 6 and have you guys grow blueberries instead.
Yeah, you're going to plant your blueberry patch right here.
Yeah.
Here's a question about that experiment, though. Obviously there are times once you've overcome the lime in the system, when you're applying that elemental sulfur, is there an opportunity to kind of blow right by the pH that you want and kind of move into like a really acidic territory by doing this, and then almost get into a situation where you've got issues with aluminum toxicity now? Or how does that work with that reaction in the soil?
Yeah, you are creating sulfuric acid, and if you ended up applying too much elemental sulfur, you could completely burn through that carbonate buffer. Because again, this is free lime, just like on an acidic soil, they apply lime, so we're just doing it in the opposite fashion. And if you overdid it, you could absolutely acidify that soil. And I've seen some scary cases, usually related to home gardens, because in a home garden, you can easily overdo it, because if some is good, more is better, right?
Absolutely.
And there have been pHs down into the 3s. Like, you could still grow blueberries at 3, but there's a case that came across my desk this winter where I saw a pH of 1.8.
Oh my God.
There's nothing that will grow at a pH of 1.8. That soil is basically swimming in sulfuric acid. So yeah, you can't overdo it.
I just want to make a note that actually I saw a place out in the state of Washington a few years ago where there were some individuals that were trying to play around with blueberry production. State of Washington is just absolutely so interesting with their agriculture system out there. They raise so many different crops. It's interesting, but they were trying to play around with blueberry production, and they actually were applying sulfuric acid, real sulfuric acid, to acidify their high pHs to raise blueberries, and they blew right past the buffer, the calcium carbonate buffer, and nothing grows there. And there is no source for lime. So it is an agricultural field that has now an acid issue.
I think this is a great example to bring us back to the importance of precision soil sampling, right? Like even here in the Red River Valley of North Dakota, there are fields that will vary in terms of percent calcium carbonate, maybe up to 4.5%, and may have those sandy areas with lower pHs, acidic soils. I know just north of my place, east of Northwood, there are soil pHs that are below 7, below 6 even. And here too, near Halstead, Minnesota, Hillsborough, North Dakota, those fields do exist. And so even though we might think, or say we got a composite for a 200-acre field here in the Red River Valley, if you put 40,000 pounds of elemental sulfur across it, sure, you might end up reducing pH a little bit, but there may be some places where that is just way too much too. and you don't know until you break apart that field and really understand what areas need that product and which areas don't.
To that point, I have gone out and grid sampled. It was a section, but I grid sampled it as 2 half sections in the same year. But it was a lot of soil sampling. Anyway,
I have like flashbacks.
Oh yeah, totally. That's why I sold you that Wintex. But in that half section, it was an interesting field because there was a ridge in the middle of it where the soil texture and the soil type changed. But the outsides of that field had a vertisol, Fargo clay type soil pHs of 7.8. But when you move to the center of that section, the center of that field, where the soil type changed, it would get much, the soil texture changed to have less organic matter, a more sandy soil texture, and the soil pH dropped. And when I soil sampled out there on the grids, I was able to find soil pHs of 5.5 in that center area. This is right off a couple miles off of I-29 in eastern North Dakota, the heart of where you would think calcium carbonate and managing iron chlorosis on high soil pH, high calcium carbonate equivalency, high lime soils would be. And yet here's this low soil pH right in the middle of that field. So interesting.
And it's probably not even, I mean, it's more than just pH, because like when you have that textural change, again, you're right in the heart of the Red River Valley. We got high K soils, right? You're probably discovering some rather low K soils that are in the 100 to 120 part per million range, surrounded by stuff that's 300-400 part per million.
Try 66.
K management's going to be a little bit different, right?
Yeah. Try 66 parts per million.
Ooh, boy.
Up to, 250, 275 in the same quarter.
That's a great point, right? Like we have more than just variability of pH too. We also have a ton of variability in potassium, which I think is an underappreciated nutrient here in North Dakota, and an underappreciated potash, an underappreciated fertilizer here that we probably should take a little bit more time and energy thinking about and fixing.
Yeah, we've done wonders of exporting potassium from this state over the past 40, 50 years. And it's only now that, the frequency of soil tests coming back less than 200, some people are starting to see K guidelines showing up on their soil test report. And for some, they've been in areas where they've been applying potassium for decades. But for most, it's a new nutrient to include in their fertilizer budgets. And again, not the whole field is going to require it. So if it's going to be a new expense, I know times are tight. So that's why precision soil sampling for these nutrients is more important than ever.
To that point, I also want to bring up something interesting that I think is going on with potassium, especially in our neck of the woods in North Dakota and northern Minnesota, from a standpoint that, prior to 2021, we were kind of in a very deep wet cycle. And throughout most of my career, of course, part of this is culture, just that we never really thought about potassium in the same way that we're starting to think about it now. But in those wet years, we just didn't see the same volume of potassium deficient fields as what we did all of a sudden in 2021. I got a ton of calls about potassium. I don't know, John, if you saw any differences about the calls that you had in 2021 for potassium in a drought.
Yeah, certainly last year as well, being another dry year, a lot more K questions.
So how is that, John, Mr. Potassium Renaissance man? What is it about wet and dry soils that makes such a difference to the potassium availability of plants?
Yeah, so it's kind of two parts. One, you have the soil side and you also have the plant side. So often when we talk about potassium, like one of the first things that ever gets mentioned is its role in water regulation in the plant, which it is very important for. Now, what is interesting is it does not prevent drought stress, but when you have plants that have enough potassium in them, so in other words, you got sufficient K levels, they have a higher water use efficiency for every inch of water that you are getting. So for what limited water you have in a drought, A potassium sufficient plant is going to get more plant biomass and higher grain yield. So that's actually how the water use efficiency component comes into play. It doesn't stave off drought stress. You just get better yield for what limited water you do have. But on the plant uptake side, potassium moves to plant roots through a process called diffusion. So it's a slow process by which the potassium ions have to diffuse through water films around soil particles to get to that plant root. So if you don't have very much water, those water films get to be very thin and tight around all the soil particles. And as a result, that diffusion path gets to be longer and slower. So under water limited periods, the K uptake rate is going to be reduced. So you have a lack of availability, or I should say is you have slower availability in soil, and the plant is also not going to utilize that water as efficiently. So it ends up being kind of like a twofold problem when you run into these dry years. So that's why when we get into dry years, it's very important to have K there already. Trying to do rescue applications in a drought doesn't usually work because you still need potassium to get that potassium that you just applied in season through the soil to that plant root as well. Foliar uptake in plants for potassium isn't very effective because it isn't like 1 or 2 pounds of K is going to fix the problem. The amount of potassium that's needed is like 20, 30, or 40 pounds of K. It's like on the same order of magnitude as nitrogen. Putting on 1 or 2 pounds of N isn't going to fix an N deficiency. Same story with potassium as well. So that's why we got to be a little bit more aware of it from the get-go at the beginning of every season, because we don't know if it's going to be wet or if it's going to be dry. But the one good thing is potassium is an immobile nutrient, so it's not going to leach away like nitrogen will. So that means we can bank on it into the future.
That was awesome. That was I just always thought that was so interesting how questions would come in and droughty years for potassium more so than the wet years. So that was really interesting.
Is there anything else you want to talk about potassium or anything else that we haven't covered here that you'd like to touch on before the end of the episode?
Well, I fear if we were to start on something else, we'd have to add another half-hour segment. So we better wrap it up. It's always too much fun talking with you two because there's so many good soil topics to nerd out about, whether it be sampling or testing or nutrient management or all the fun things that we get to experience throughout the year. So no, we'll just have to save it for another day, I fear.
That's just fine. We'll have another conversation because we haven't even had the chance to talk about the actual mechanics of soil sampling out in the field and actually pulling good cores and those kinds of things. That could be a whole nother half hour.
Well, that's good because there's plenty of equipment to talk about.
Awesome. Well, hey, thank you so much for the conversation today and for the episode 2 weeks ago. Again, thank you so much for the time, John. We really appreciate your expertise, and we know that our audience will too. With that, remember with GK Technology, we have a map
And an app for that.
No, I can't wait to get in the fields again.
Let the geeks at GK Technology help you with your agricultural data. Their agronomists know agriculture. When it comes to creating soils and zone maps to maximize yields in your fields, you can trust the people with decades of experience in site-specific agriculture. Everyone at GK Technology has a background in agriculture, so they know what makes a farm run, and they speak your language. The geeks at GK Technology have a map and an app for that.